Hello, my name is Leigh Orf. I'm an atmospheric scientist at the University of Wisconsin in the United States, and I'm going to talk to you today primarily about simulations of downburst using computer models. But first, before I get to the computer aspect, I would like to give a background on the physics of microbursts, because as a scientist, it's important that we look at what causes these things so that we can create accurate models to simulate them, to do work such as what we do in engineering, where we take models and we run the atmospheric air into buildings or whatnot to see what kind of loading occurs through different kinds of wind forcing. So that's the ultimate goal of a lot of wind engineering CFD work. It's great because you can create your little virtual laboratory and knock down virtual buildings before you have to knock down the real ones. It's similar in atmospheric science, where we will observe the atmosphere with our remote sensing devices such as radars, thermometers, all those barometers, all those different things, and then we can simulate as well and compare and improve our models and maybe learn something in the observations that we discovered in the model. That happens in atmospheric science. But I'm going to talk to you today more. I understand the audience is wind engineering or engineering audience, and I have collaborated for a long time. I've had a very fruitful collaboration with Dr. Eric Savory at Western University in Ontario, Canada. He and I have been collaborating for about 15 years now, and I have a pretty good idea as a atmospheric scientist of how wind engineering works, but you'll definitely get my own perspective on this as we go along here. So first, I'd like to acknowledge the ERC and the EU for supporting this conference, as well as the National Science Foundation in the United States for supporting my research. Okay, so today I'm going to talk to you first a bit about some history. It's good to understand sort of the history of these features. In my opinion, it gives us some context. Give you some basic thunderstorm background on what causes downbursts physically, and then look at the wind engineering approach to studying downbursts. There is more than one approach to studying something like a downburst. In the case of wind engineering, you're primarily interested in providing a good model of these things so that you can design buildings and structures to withstand them under certain load scenarios that are caused by them. There are a couple of ways that microbursts are simulated in wind engineering, a couple of popular ways, and I'll talk about those two different ways. And then I'll talk about the physical way, which is the approach I prefer, which is actually having a full cloud simulate the storm and then letting the downburst form out of the storm. You don't really know how it's going to form or what it's going to look like, but that's, I think, a more physically accurate way of doing it. Not to say that everyone should be doing it, because it's just it's not practical. But we'll talk about that in this section, and I'll talk a little bit about where I think things are going in the future. So you can't talk about downbursts and microbursts until you talk about Ted Fujita. He was a pioneer in many ways for understanding the damage caused by downbursts and the damage caused by tornadoes. He was a very crafty primarily observational meteorologist, who then would, and he was very uniquely gifted in this, he would look at the damage from tree falls, building falls, whatever it was, whether it was from a thunderstorm. Well, this is the point. He didn't know whether it was a thunderstorm or maybe a tornado producing thunderstorm or a downdraft producing thunderstorm, downburst producing thunderstorm. So he saw patterns in the damage that some of them looked rotational, like you would expect from a tornado, but some looked like someone had sort of dropped a bomb and there was divergent motion, divergent damage patterns, things falling outward instead of spiraling inward. And Fujita hypothesized quite correctly that this was caused by downbursts or by downdrafts from thunderstorms. And this was met with intense skepticism at the time, because downdrafts were thought to be broad and diffuse primarily. Nobody had ever observed or theorized, I think, downdrafts being that small and causing that kind of damage. So Fujita helped, from his very dogged work in convincing the community that these things were real, he did get funding to spearhead some field studies, because in meteorology, you got to go collect data if you're going to convince meteorologists of what's going on. The first program was called NIMROD, Northern Illinois Research on Downbursts. So this was in a more humid climate. Northern Illinois, where I grew up actually during my high school years, is in the summertime especially, can get very humid, and you get some pretty powerful thunderstorms. You're probably going to get what are called wet downbursts or wet microbursts in an environment such as north central Illinois in the United States. He also spearheaded a program called MIST and JAWS, a Joint Airway Weather Study in Colorado in the western United States. Now, this is where your dry downbursts tend to occur. The classic environment for a dry downburst is one that occurs in places like Colorado in the high plains. And then there was another program called MIST in Alabama, which is even more humid than Illinois. So we're talking probably mostly wet downbursts down there as well. The boundary layer just tends to be more humid, and the forcing for downbursts tends to be more from precipitation drag in these very humid climates than what we see in dry downbursts, which are primarily buoyancy forced from thermodynamic processes such as evaporation and melting, and some sublimation as well. So following Fujita's discoveries of real downbursts, then they started putting radars at airports, because a primary reason for studying downbursts is the wind hazard they present to aircraft in the landing and taking off stages of flight. In the 60s and 70s and even 1980s, it was not all that uncommon for aircraft to crash in the case of experiencing thunderstorm winds from downbursts. In other words, pilots had not yet been trained on how to deal with downbursts, or they weren't even aware that they existed. So there were some pretty high-profile airline crashes in the 70s and 80s that were due to aircraft encountering wind shear. So what Fujita realized was, if we can install radars at airports and train pilots to understand these and train everyone on what downbursts are, then we can avoid them, because they don't last very long and they're always spawned from thunderstorms. So maybe we can just avoid them. And in fact, in modern times, in the 21st century, 2021, where we are now, I'm not aware of any air shear related aircraft hazards that have occurred in the last 20 years, maybe even. So that's a really good thing. It's one of those solved problems, you might say. Aircraft, just pilots know how to avoid them. But it was a huge motivator for understanding downbursts in the earlier days, in the 80s and 90s, because of what they did to aircraft, or what they could do. Now, in the modern days, we're still interested in wind shear hazard, but we know how to avoid it. But now the focus on downbursts from the scientific side, from my side of the coin, so to speak, is understanding how their nature in thunderstorms. You know, they're embedded in thunderstorms. I study thunderstorms that produce tornadoes, but there's downbursts often spawned in different parts of the storm. So I'm interested in the damage that downbursts cause, the winds, the strong winds they cause. So I'm interested in faithfully simulating downbursts that occur in real thunderstorms, and hopefully that research will continue. So it's, when you look at downbursts, there's some terminology we should get across. A downburst is simply a strong downdraft inducing an outward burst of damaging winds on or near the ground. A microburst is a downburst that has a damaging an outflow region where you can identify it that's less than 4 kilometers. A macroburst is greater. I will interchangeably use the term downburst and microburst. Macroburst these are just sort of the technical terms if you want to be pedantic. In all cases, they produce horizontally divergent surface flow, or quote-unquote straight-line wind damage, or straight-line wind patterns. So here's a nice view of a downburst occurring from an air mass thunderstorm, and this is out in Arizona. You can see the saguaro cactus off there in the bottom right of the picture. And if you sort of can imagine what the wind flow might look like, that's basically what you're seeing to a certain extent. In this case, you can see dust being kicked up on the leading edge of the outflow that suggests a roll vortex, perhaps moving outward. Here is another storm. This is I believe in Phoenix, Arizona. showing a time lapse of a downburst occurring. Now, this is probably technically a wet downburst, but you can have some rain fall on the ground with a dry downburst. It's just that it can't be a certain amount. But the same kind of thing in the monsoon season of Arizona, the southwestern United States, they do experience something of a monsoon, and in August, July and August, you'll often get these beautiful thunderstorms, very photogenic, lots of lightning, often producing scenes like this. So here's another wet downburst occurring embedded within a thunderstorm, and this view just happened to catch the light. The light just caught the outflow, so it's a really rare view that you get in this sequence here. And you can see that there's definitely something going on along the leading edge of that air once it hits the ground. Here's another nice view. This would also be, I'm pretty sure, a wet downburst. You can just see the rain shaft as this storm moves over the river, the lake here, and then just boom. It's like a waterfall of water. And you can even see some interesting shear instabilities occurring along the leading edge of the rain as it falls down to the ground. So this is what it looks like in nature, some classic downburst or type thunderstorms, or thunderstorms that might produce them. Now, Fujita studied the damage patterns left over by downbursts. So here we go with some tree falls that were observed in 1974. This was actually one of the largest tornado outbreaks ever. In the United States, pick anywhere in the world. And this is where Fujita went out and looked for damage patterns, and he saw stuff he didn't necessarily expect. Tree falls that were divergent as opposed to rotational. And rotational damage is what you'd expect from a tornado, not from a downburst. Notice also here on the left in a cornfield in Indiana, look at the black arrows that he's indicated there. So that looks like a fan-like motion of the air as the downburst hits the ground and spreads out, but it doesn't spread out axisymmetrically. It doesn't look like a nice idealized ring that goes around it. And that's due to the messiness of reality and the fact that the storm is moving. We'll talk about moving downbursts in a moment. On this right image here, it looks like a downdraft hit the top of that shed, which has a slanted roof, and then just had like a burst swath, is what Fujita called those. You see them in the cornfield there. Here's some pretty stark evidence of downburst in northern Wisconsin in 1977. Look at how all the trees are falling towards the left in that case. The downburst hit the ground and just knocked those trees down. That is not tornadic damage. Not even close. All the trees are laid down in the same direction. That's straight line winds from a strong downburst. And here's a schematic that Fujita put together that sort of exemplifies, or it gives you an example of the difference between these two types of damaging flow features. On the left, you have an idealized schematic of a downburst. On the right, you have an idealized schematic of a tornado. And I say idealized schematic because in the real world, things are much messier than this. For instance, you often don't see a nice clear horizontal ring vortex or a roll vortex on downbursts, at least that I simulate. And in a tornado has multiple vortices, and it has horizontal vortices and other things going on. But this is just basically the difference here. Notice Fujita shows the strongest winds beneath the roll vortex. He indicates up to 100 knots, 100 nautical miles per hour. That's pretty fast. We're getting into the upper 30s meters per second, 40 meters per second. And on the right, you see he indicates maybe winds as high as 150 knots. We know that tornadoes can exceed easily, but occasionally can exceed almost 280 knots, maybe 300 mile an hour winds have been observed. So this is just sort of giving you an idea of where the strong winds are. And in the case of the downburst, we're looking at strong winds that are primarily straight line winds. They don't always occur in a nice symmetric way. So as I said earlier, the main reason for studying downbursts really had to do with the fact that they were an aircraft hazard, and we needed to understand their dynamics better so that we could forecast them. And then the goal was we just wouldn't have pilots encountering these anymore. You can always fly around, do another pass before you land, and it's an inconvenience, but everyone is safe. So I will, though, briefly show you why downbursts are damaging to aircraft. Here's an analysis by Ted Fujita in one of his books Notice the glide slope of the aircraft as intended is the dashed black line. The actual slope of the plane as it tried to land in this downburst is shown in the red line. Notice it does encounter the ground. In other words, it does crash in this case. In this case, we had a microburst interacting with a sea breeze front. And I actually did some research or some simulation work on the dynamics of that kind of encounter in my own work. Yes, it will produce a hazard regime in the collision region, but you also have your classic damage or your classic hazard from just the downdraft itself. The downdraft just pushes the plane down, pure and simple. A tailwind, because of the way that planes stay in the air, you know, they have to go into a headwind to get lift. Well, if you have a tailwind, you lose lift and you crash. You don't want to give. It's like flying a kite. You get a tailwind with a kite. You're flying a kite, and the wind shifts and comes at you. The kite goes blah, 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 blah. It's not gonna stay aloft. So what we learned in some of our field programs was that this is the Nimrod and Jaws studies. Is that a typical microburst? First of all, they observed a bunch of them. That was huge. Okay, we actually they observed them. They were very common. Some were strong, some were didn't really cause damage. But these types of small, intense downdrafts occurred. We saw them with radars. We saw them with our in situ devices. Typical microburst winds 4 meters above the ground because that's where they would have placed the lowest wind sensor. About 20 meters per second. Maximum observed during these programs was 33 meters per second. Okay, not the worst damaging wind in the world, but certainly implies there could be some wind shear that could certainly cause a problem for aircraft. In this particular set of studies, they saw surface temperatures that ranged from minus to positive 4 degrees Celsius. So sometimes the air was warmer when it hit the ground or colder, and we can talk about that in a minute. Surface dew point temperature, which is a representation of how much water vapor is in the atmosphere. Sometimes the air was drier, sometimes it was actually moister when it hit the ground from the downburst than the surrounding atmospheric air. And we know now from our field studies and our numerical work that primarily the forcing for downbursts and microbursts, macrobursts, all those bursts comes from thermodynamic cooling and mass loading. Thermodynamic cooling occurs when the rain that comprises a downburst is primarily rain, maybe some snow in the upper part, or even some hail. When the rain melts, when the ice melts, such as the hail and the snow, that's a thermodynamic cooling process. When the rain that forms from the melting of the hail and the snow falls and further encounters dry, warm air, it will evaporate. And the very strong forcing for downburst is evaporation of rain. So I want you to understand as wind engineers, if you're going to do modeling work of microbursts, you should be aware of these things. Because how you simulate your microburst or your downburst, you should keep in mind that they're primarily buoyancy forced, and that they often, for the wet ones anyway, are forced by the drag of the precipitation. So then the key is how do you parameterize those things, or how do you simulate those things in a simpler model? And we'll talk about that in a minute. So we should talk about the difference between a wet and a dry downburst. In the case of a wet downburst or microburst, as it implies, heavy rain accompanies these. Wet downbursts tend to occur in thunderstorms that have low cloud bases, lots of available water to squeeze out of the atmosphere in the form of rain, and maybe, just maybe, a very shallow, dry adiabatic layer near the ground. In other words, there might be a layer near the ground that is conducive to vertical motions. And we'll talk about atmospheric stability shortly. But you can't just push air up and down in the atmosphere and expect it to keep going. That only happens under certain conditions. So before we get to that, just take a look at these three images. The wet microburst on the left, notice the cloud base very low. Let's look at the one on the right. High cloud base, very dry, well-mixed boundary layer. In this case, you're going to have precipitation that probably evaporates or entirely evaporates before it hits the ground, and that's called Vega. When precipitation, such as rain, falls, you can see it falling, and then it, poof, never makes the ground because it all evaporated. Or in the case of snow, sublimated and then melted and then evaporated the rain. But you can still have a pretty strong downdraft hit the ground even if you have Vega. So don't let the wet microburst fool you. And in fact, having a nice deep dry adiabatic layer gives some distance over which that air can accelerate if it's under negatively buoyant conditions. So here's some observations from radar of one of the Nimrod downbursts. On the left is a vertical cross section showing you the winds in the plane, the vertical plane that this slices through. You see the blue indicating downward winds exceeding 13 meters per second towards the ground at, say, about 800 meters above the ground. Strong downdraft, it's not symmetric. It leans a bit towards the right. So as you see on the right image, the horizontal wind speed, that's a classic outflow pattern I've seen in many of my simulations of a strong downdraft. It's asymmetric, meaning the strong winds are all going towards one direction. In this case, they're all going towards the right, and that is where your damage is going to occur if a building or something encounters a downdraft. It's probably just beneath a developing roll vortex, and so yeah, that's primarily why, what we look for in downbursts. Very small region, small as opposed to, say, synoptic scale winds, from, say, a hurricane or an extratropical cyclone. This only occurs over, say, a kilometer. So it's small and it doesn't occur for a very long time. Short-lived, small phenomenon. Very difficult to deal with, right? That's why engineers are like, well, they're not common, but we should be at least able to survive a certain threshold of downburst or strong wind, right? You don't want to just think, well, it's pretty rare, so who cares, right? That's not a good plan either. Here's another observation of a microburst. This was near Denver, 14 July 1982. Vertical cross section again. You can kind of make out what looks like, downward, and then one side here, you got one side there. It kind of looks like what you'd expect with the downdraft and some outflow. When you look at images like this, by the way, when you look at Fujita's analysis, he just did the most stunning analyses you'll ever see anywhere, I swear. But a lot of his own model of what was going on sometimes is built into these things, such as the black arrows showing the motion of the wind, of the air. There's some I wouldn't say artistic license, say scientific license here. The radar is giving us the reflectivity and some radial velocity, but everything else, there's going to be a little bit. This one's actually probably one of the ones where he did the least amount of guesswork, shall we say. But no, he was almost always right. I'll say that much about Fujita. But there you go. You don't want to encounter that. In this case, the pilot abandoned the approach and went around, and all was well. And that's exactly how things are done today. So you should always feel safe flying when it comes to downbursts, because pilots just avoid them, and they're easy to avoid. Okay, so one of the most, probably the strongest downburst ever observed by an instrument, in this case an anemometer, occurred shortly after Air Force One landed at Andrews Air Force Base. This was in 1983. President Reagan at the time had just landed minutes before, and then this monster downburst just blasts the airport. We had the maximum wind observed in this event was 67 meters per second. And you can see the trace of the wind from left to right. That first peak is the outflow head encountering the instrument, and then the null is as the downburst passes over, you have flow in the opposite direction, and that's sort of the stagnation point. And then 3, you have another gust in the opposite direction, as the opposite side of this thing, even though it's moving away from you, still has a significant amount of velocity. So yeah, this was an amazing event. This is probably, I don't know, I wouldn't put a number on it, once in a long time. Chances are these things don't happen that often. This one just happened to get caught perfectly by the anemometer. But now you're talking some serious damage from something like this. That's going to do some damage. Okay, so again, this has all been Ted Fujita's work, and I have to talk about Ted Fujita before we talk about downbursts, just because of all the important work he did and how he came to his conclusions. An interesting thing about Ted Fujita, as opposed to a lot of other scientists who study severe weather, is that most of his work was actually published without peer review. He sat in his office and wrote these reports, and he published them through the University of Chicago. And he's got dozens and dozens of these things. They're all on the Texas Tech is a university in Texas here in the United States. They have they have his collection all digitized, and you can get it for free. So keep that in mind. I'll put there's going to be some supplemental material at the end of this talk that I'll give you some links to these. So sometimes Vegeta didn't get everything completely right. It took years and years for us to sort of discover these things, and obviously, because a lot of the events that he was analyzing, well, they all happened, it's impossible to completely know what happened, right? But we can sort of bring some of these storms to life, or some of these events to life, with numerical techniques. And yeah, he had one particular storm that I studied for my PhD thesis that involved a crash. His analysis was that there was a concentric downburst just sort of pumping downbursts into one area, leading to several world vortices, etc. I tried to simulate that during my work, and I couldn't get it to work. My advisor did, actually. I'm pretty sure he tried this out, or we did it together. It doesn't matter, because the point was we realized we had to find another explanation for that, what happened during that crash, because we had the black box from the aircraft, and Dallas-Fort Worth Delta 191. That's the one you want to look at. My work at least suggested there may have been another scenario that explained what the aircraft encountered. So this is a diagram from one of Vegeta's books where he shows, actually it's on the cover, or the first page, I think. It's an artist's depiction of how he thought the Dallas-Fort Worth 151 analysis, or what environment it occurred in. Now you'll notice the main thing you see here is this big cloud in the foreground with concentric rings from concentric downbursts. That didn't happen. It doesn't work that way. You don't get concentric downbursts when you actually force a microburst like that. What happens is the air just basically encounters air that's already moving outward, and it doesn't form the roll vortex head. It just kind of there's like a bump, if anything at all. Now, if you look in the background of this diagram, way in the background, you see another storm back there. Now, that's actually representative of that environment. There was another thunderstorm not too far from this one. So what my advisor and myself, over time, we sort of came up with an idea. Well, let's see what happens if you have one thunderstorm here, or one thunderstorm producing two downbursts, or two different thunderstorms producing downbursts, and the air interacts as it encounters. They encounter each other, and what happens when that happens, right? Could the wind field be hazardous in different ways that we don't already know or understand for aircraft? That was the main goal here. So that image is nice, but I think he got it wrong. And here is his analysis, a vertical cross-section through that image that you just saw. You'll notice there's roll vortex 1, roll vortex 2, roll vortex 3. The reason he hypothesized this was when he looked at the black box of what the aircraft encountered, he was trying really hard to find a way a single downburst could have led to those winds, and he came up with this. Alternatively, it's possible that there was another type of event that happened. So I'll talk about that in a little bit. So as we we're getting towards the CFD part of this lecture, I wanted to sort of get down to the basics again, so you understand how downbursts really form in the real atmosphere, so that if you go down the road and you want to simulate a downburst for your research or for designing a building or whatnot, at least you understand, have a basic understanding of the physics behind the downburst, so that when you choose your model, you'll know, okay, we're going to use an idealized model. It's not going to have this item in it, perhaps, but we can get away with it because blah, 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 blah. But at least you understand, and maybe you could even improve your model if you think that including things like cold air, for instance, instead of just a blast of air that's the same temperature, maybe that's a good idea. So downbursts are formed from thunderstorms, period. They don't form out of the clear sky. They don't form out of anything but a thunderstorm. Okay, so you've got deep moist convection, or even shallow convection, but you need convection. Clouds growing vertically, and thunderstorms produce the downbursts via all this thermodynamic stuff primarily, and also the dragging of rain as it falls. So those are the two formation mechanisms, the thermodynamical processes, and you can just, you look at a chemistry book and you go whatever you want on this. Sublimation, melting, and evaporation are the cooling processes that occur when water changes phase. Deposition, freezing, and condensation are the warming ones, and those occur normally when the cloud is growing before it all comes down. So if you have, under certain conditions, and not always, if you have a really heavy rainfall, it doesn't mean you're getting a wet downburst. It does not work that way. Under certain conditions, wet downbursts will occur, and they appear to be forced primarily by just heavy rain over a small area, like in a rain shaft. But it also helps if you have a relatively unstable atmosphere, so that the atmosphere doesn't essentially push back and lower the speed of the downdraft before it hits the ground. So the types of environments that are conducive to downbursts basically are the types of environments that are conducive to free vertical motion. So you want the atmosphere to be free vertical motions to occur without a whole lot of work. If you have an unstable environment, okay, you're talking about the environment. Think of what the type of environment the storm's going to occur in. If it's unstable, it doesn't take much to kick off a storm, or it doesn't take, the atmosphere isn't going to slow down your downdrafts as they encounter the ground. If you have a stable boundary layer or a stable environment, it's going to be like the atmosphere is pushing back like a spring. If you move the air upwards, it's going to try to push it back down. If you push the air downwards, it's going to try to spring it back up to its original location, and that is a stable atmosphere. I will say now the atmosphere can be stable at the bottom and then unstable and then stable, so it doesn't have to be the same everywhere, and it rarely is. So one type of phenomenon that occurs occasionally is called a heat burst. A heat burst is, as its name implies, an intense downdraft that hits the ground, spreads out, but it actually results in air that can be like 10, 15 degrees Celsius warmer than before it happened. Heat bursts are probably occurring when you have a strong buoyancy-forced downdraft aloft, and that air is accelerating downwards. It's cooler in its environment, accelerating downward. Then it encounters a very intense low-level inversion where the atmosphere's temperature increases with height from the ground, and suddenly, by virtue of its momentum, it just keeps going, but it's being adiabatically compressed as the air sinks, and the air that once it hits the ground is actually warmer. So it started out colder than its environment up there, say 500 meters above your head. Maybe that air was 5 degrees colder than its environment, sinks to the ground, encounters that inversion, and poof, it's warmer than its environment. But it still had enough momentum to punch through that stable layer. But what we really want for downbursts is a deep, well-mixed, dry adiabatic layer near the ground. That is a classic setup for at least a dry downburst. And here is what's called a Skewt thermodynamic diagram. It is a diagram that shows the relationship between things like potential temperature, and pressure, and mixing ratio. On the left, you have the vertical coordinate is pressure, so pressure decreases with height, but it's pretty much linear in Cartesian space. So you look at height above the ground. At 100 millibars, you might be, say 12 kilometers above the ground or so. So taking a look at this, notice the straight line that says deep, well-mixed layer. That is the layer where the falling rain will evaporate and accelerate before it hits the ground in this environment. On the left, that is the dew point trace. The one thing to realize is at the surface of the ground, the dew point's a bit higher. We do need to have enough moisture in the environment to actually grow the cloud. So you sort of have this case where you have a deep, well-mixed layer near the ground, some moisture so you can grow a cloud, and then above that deep, well-mixed layer, you're going to encounter, you can't have this dry adiabatic layer extending out into space. So eventually you encounter some stability, but so long as the atmosphere has enough instability to grow that cloud, and you see I sort of sketched a little cloud there, that's where it would grow. If it were to grow, then it produces rain and snow and hail, and then that falls through our deep, well-mixed layer, our dry adiabatic layer, and then all the thermodynamics kick in along with just the physical dragging of the air. They call it mass loading. And that's the other thing that will cause or help to force a downdraft. Okay, so let's look at some equations, shall we? Everyone loves equations. So what I'm doing here, and again, this is in the supplemental material, I'm going to just show you a little bit of Navier-Stokes type equations to show sort of where downbursts are forced physically. And these are taken from the model's equation set that comes with the model that I'm using. These first three equations, U, V, and W, are the east, west, north, south, and up, down components of the wind. So what's going to make the wind blow? All right. The first term in all three of these equations is the pressure gradient force. It's variations in pressure, either horizontally or vertically. On the right-hand side, you have advection, AdV, Coriolis force on the two UV terms, and some other terms. I want you to focus on the third equation, dW dt. The second term on the right-hand side is capital B, and B stands for buoyancy. And if you're looking at what force microbursts, you're looking at that term because you're looking at dW, which is the vertical component of the wind, dt over time. So acceleration in the vertical. What is going to change? What is going to change W? What kind of accelerations are we going to expect from buoyancy? Now, if you look down to the bottom of that equation set, the buoyancy is listed out in equation form. It's a very simple formula. You have gravity, 9.8 meters per second squared on the left-hand side, because without gravity, there's no buoyant force. Let's not think about that. We don't have microbursts in space. We don't think we do. But anyway, so the first term in the brackets is potential temperature perturbation divided by the base state potential temperature. At a horizontal level, let's say we're near the ground, you can replace potential temperature with just temperature, as long as you actually put temperature at that level in the denominator as well. So one way to think about this is, buoyancy. This is about buoyancy. If you have air that has a lower potential temperature in it compared to the surrounding atmosphere, that means theta prime is negative. That is going to cause buoyancy to be negative, and a negative term on dW dt means we're forcing downward motion. So thermodynamic cooling, that's that first term after the bracket. The second term, 1 over epsilon minus 1 times QV minus QV naught, that is perturbation water vapor in the atmosphere. Dry air actually is heavier than moist air. This is something that meteorology students have a hard time understanding. Water vapor has a molecular weight of H2O, 18 grams per mole approximately. That's smaller than nitrogen, right? Roughly 28 grams per mole compared to 18. So if you evaporate water vapor into the air, you're lowering its density. And dry air surrounded by moist air will actually give you some negative buoyancy. So you'll actually have, the dry air will give you a downdraft or help you have a downdraft. So we have cold air surrounded by warm air gives you a downdraft. Dry air surrounded by moist air can also give you, or at least help you form a downdraft. The terms, it's forcing you down. Okay, it's forcing you into a downdraft. Now, the next two terms, Q sub L and Q sub I, are liquid water. Now we're talking liquid water, so water H2O, 1,000 kilograms per cubic meter density, right? Rain. We're talking about rain in this Q sub L basically, and Q sub I would be all ice hydrometeors, so snow and graupel and hail. So if you have rain falling, that's going to help drag the air and cause a downdraft. If you have graupel or hail falling, same thing. So again, the buoyancy forcings for downbursts are temperature colder than surrounding air, air drier or water vapor lower than the surrounding air, drier air surrounded by moist air, and then just rain and hail and snow will all help to increase the negative buoyancy of the air. Okay, and that's kind of intuitive for once, right? The dry, moist one's not intuitive, but certainly you can imagine the buoyancy being higher when you have a lot of rain and mostly it's rain and hail. Finally, looking at the equations, and again, this is here for illustrative purposes mostly. You look at the equations for the liquid water and the ice, but more importantly, look at the d theta prime dt term. That's the, are we cooling the air? Are we warming it in potential temperature terms? There's a whole lot of terms. The ones that, the bottommost line, you have the latent heat of vaporization, sublimation, and freezing. Those are all the phase changes. So you have phase changes change the potential temperature, which changes the buoyancy, which gives you updrafts and downdrafts. So that's the deal with what really forces downbursts. It's all about thunderstorms. And here is a nice schematic of what we call a cold cloud in the United States. Think of a thunderstorm cloud. Follow the red arrows upwards. That is the cloud growing vertically. You have condensation occurring, which is a warming process, makes the air more positively buoyant. Eventually, you have freezing, which is also a warming process. Lots of ice growing in the cloud, and the Bergeron process kicks in. You create a lot of snow. Eventually, you create mass that's heavy enough that it falls under its own gravity, under its own mass. Snowflakes and things, some of these things have very small terminal velocities, but as they get bigger, they fall faster. And then they melt, and then that's a cooling process. The melted water is now rain. It evaporates. That's a cooling process. And then if it doesn't all evaporate, you get rain on the ground. But this is kind of a real quick back of the envelope schematic of how a thunderstorm works, at least in terms of its microphysics. And how does it look in a computer model? Well, it looks like this. A bunch of spaghetti and meatballs, I guess. So all I want you to take away from this diagram is the schematic nature of it. You have water vapor, cloud, water, cloud, ice, rain, snow, graupel, and hail. And you notice it's all basically buckets and arrows, buckets with drains in them, and then spigots to fill the bucket. You can either, for instance, if you have some water vapor in a bin in a model grid zone, and you start forming some cloud water in that grid zone, you're probably stealing from the water vapor and putting it into the cloud water bucket. And you're conserving water mass. You're just taking it from gaseous form into liquid form. So microphysics is all about keeping track of the water. You have to be really careful in your microphysics. Now, as engineers, you're probably not going to encounter this type of thing unless you start using full atmospheric models. In that case, I would encourage you to collaborate with an atmospheric scientist. We're out here. We'll collaborate. But seriously, you don't want to black box it. You don't want to use a model that's complex and not understand what's going on. I don't claim to know everything that's going on in these models, but if you look at a figure like this, and these are all published and the source code is out there, you can imagine that it's pretty complex. And the microphysics part of a model tends to be the part that is the weakest link, I think, if we're looking at how to improve our forecasts and such. But that's how it works in a cloud model. And that is how I've been modeling them to a very large extent. I use a cloud model that has all that messiness in there to force my downbursts. So, okay, approaches towards simulating downbursts include physical models. So, and you have more experience with this than I do as engineers, I think. My collaborator, Eric Savory, he's got these rooms where he has these tanks, and very carefully controlled denser fluid is released into a tank surrounded by less dense fluid. You have lasers watching everything and modeling this thing. So you scale the atmosphere down to another flow feature that has similar Reynolds number, and you look at what goes on in the tank. Then you have an accompanying CFD model to model what goes on in the tank to compare. So your tank model, your models are in agreement. And that's typically how it's done in that I understand. I shouldn't be telling you this, but that's physical models are used a lot in engineering. They're not used as much in meteorology, in my experience. They're not. Cloud model simulations, full cloud model simulations, that's my wheelhouse. That's what I do. I use a model that grows a cloud that produces a downburst. Now, I also do the next thing. Oh, no, not the next thing. The next thing, you could also just create a model where you just have ice at the top of your boundary and you just drop it in and let the thermodynamics kick in. So you don't worry about forming all that stuff, but you just drop it as if it's just coming from nowhere. Fred Proctor did that. He was the pioneer really in understanding the strong winds from downbursts. He did it before anyone else did. I'll show you his work in a moment. So you introduce hydrometeors from the top of the domain, and then the thermodynamics kicks in, or even the drag can kick in and form your downburst. That's a perfectly good way to force a downburst. It's better than I would say it's better than some of the methods that even I use usually. Cooling source, there's the method I use mostly. So if I'm not simulating a full cloud, and this is how I did my earlier work as a PhD student, and this is from work my advisor had started, I start with an ellipsoid of cooling that's supposed to mimic what happens in a rain shaft of a cloud. So you have a cloud, here's your cloud base, you have this blob that is just basically a heat sink. So you have the air gets colder and colder and colder, and eventually gravity kicks in and it hits the ground and spreads out and does its thing. That's a cooling source approach. I've published several papers with my collaborators at University of Western Ontario on its use, and we feel it's better method than the impinging jet method, which is what I like to call pipe in the sky. You just, as its name implies, you have a momentum source of air. The air is not buoyantly forced. You don't force the air from, you don't have cold. It's a barotropic model, as I understand it. There's no cold air at all. And you just essentially jet the air down through a pipe. Now, when the air exits the pipe, it finds itself in air that's not moving, and a shear layer develops, and you get the roll vortex sort of forming artificially, I think, as the air exits the jet. And the downbursts that IJ models produce, I think, are not as useful or as good as the ones that the cooling source approach does. Although there is some argument for the use of IJ. I've seen shear instabilities form along downdrafts. I don't tend to see that in the cooling source approach, but I do sometimes see it in the impinging jet. We'll show you some figures in a minute. But anyway, this is about the halfway point of this talk. That's good. I'm going to talk for another 45 minutes or so. And now we're going to talk primarily about modeling downbursts. So the rest of this lecture will focus on the CFD part, the simulation, the numerical part. So just to get on the same page here, in atmospheric science, most of our models use explicit numerical techniques, meaning that you have everything on the right-hand side of the equation set, you solve for it, you update your variables, and you move on. And our meshes tend to be regular rectilinear meshes, so think of a cube or a rectilinear volume. The models solve, and you've seen the equation set for at least the CM1 model, some of it, but you have the three components of wind, potential temperature, pressure, turbulent kinetic energy, and all those microphysical variables if you have microphysics in your model. So here is one of the first numerical simulations I'm aware of that model downbursts at high resolution. So what Proctor did here, he used an axisymmetric model, so it's a two-dimensional model, and he introduced hydrometeors at the top of the domain and let things happen. And look at this, it's got a nice, you see the outflow, the downdraft, the horizontal outflow, and then the roll vortex, and you see also a counter-rotating roll vortex right near the ground as it encounters friction. So you have a primary and secondary roll vortex there. Now again, I want you to keep in mind when you see these roll vortices, they don't always look that way in nature. They're often a little messier than that, but yeah, they don't always look that smooth. Let's just put it that way. So Kevin Knupp in 1988 did some three-dimensional simulation of downbursts, and this is an important work because notice in the figure here, height above the ground, and we have accumulated cooling, so we're just basically keeping tabs on the thermodynamic forcing. Above the freezing layer, or the melting layer, which is about 2 kilometers, 0 degrees Celsius, it's no surprise that sublimation is the dominant forcing, because what else? You can't have melting because it's not melted, it's below freezing. So it's only sublimation. That's going from the solid state straight to vapor. You already have cooling forcing at 3 to 2 kilometers. Now look what happens once that air encounters warmer than 0 degrees Celsius air, is super freeze, or it encounters warmer air, melting kicks in, and you often see this on radar, a melting level. It really shows up really well when you finally hit that layer where it's above zero. You have melting, and melting is a cooling process as well, and you'll notice that melting is a pretty dominant process just below the melting layer, and as you approach the ground, you see that evaporation becomes dominant, which makes sense. You're melting more water substance, you have more liquid water substance, now you have more available liquid water substance for evaporation as you encounter drier and drier air, or air that has a lower and lower relative humidity, let's say, as you approach the ground. So this is good work. It really gets down to the forcing of what's going on in these things. Some work done by I used to work with Jerry Straka, and John Anderson was my advisor way back in the 1990s at the University of Wisconsin. They did a full three-dimensional cloud model at what was very high resolution at the time, and they also looked at the distribution of thermodynamic and loading forcing on downbursts. Mass loading, which is the hydrometeor frictional drag, they found it was maximized aloft at, say, 5 kilometers above the ground. The melting was maximized up above the freezing, right just below the freezing layer, and then evaporation. So their results weren't that much different than what Kevin Knupp found, which is good. That means it was 2 different models, 2 different studies, similar results. that gives us confidence in these results. Now, Strzok and Anderson did a three-dimensional model, and here is the plan view of the surface showing an asymmetric but very much clearly a downburst or a divergent outflow where you have stuff going outwards. But it's, you see to the northeast and the south, there seems to be more action maybe in those directions. There's environmental wind shear present in this environment, so we're now trying to make it more like the real environment. And this work was done in conjunction with observational work where, and I remember vaguely back in the early 90s, I would run model simulations for Jerry and John, Strzok and Anderson, and get the sounding in from Orlando, run the model, give them results, and then it went into this paper or a study similar to this, trying to see if we could forecast downburst occurrence in a hot, moist environment. Again, this was right at the tail end of pretty much, well, we understand downbursts, but we still wanted to forecast the environments where they were dangerous so that, if you work at an airport, you're aware of the types of days when these things occur, so you have a heads up. That was a motivator for that. Okay, so the cooling source approach is the approach I used in my PhD work, and we still use it today. I still use it today in my work with the University of Western Ontario, Eric Savory, and his students. And this is something that is nothing too amazing about this. This approach long precedes my own research. Essentially, whether it's a cooling blob or a warming blob, you just have an area over which you impose a positive warming to start your cloud. It's called a warm bubble perturbation, or in this case, it's a cooling source perturbation where you just slowly bring the temperature down to mimic what happens when rain evaporates beneath the freezing layer, and then your downdraft occurs. The reason why I like this approach better than, say, an impinging jet approach is that it is buoyantly forced, which is how downbursts really work. It's forced by physics. Forced by reasonable physics, shall we say. Anyway, it's a really easy approach to do, and you might want to consider using it, especially if you're looking at downbursts occurring in dry downbursts for sure. But even wet downbursts, you could always do the same thing that Proctor did and just drop a bunch of hydrometeors in there. Certainly, there's ways to make it a little bit more physically accurate than just blowing the air and not dealing with the thermodynamics. Okay, so this is for my own the first paper I wrote, my thesis work, just a vertical cross section through the heart of this downburst. This is also a three-dimensional model. I'm just showing you a axisymmetric simulation within that three-dimensional model. It's axisymmetric because that's how I forced it. The actual cooling source blob, that Q sub Q term, we made it axisymmetric so that the subsequent downburst would be. Then we're going to make things non-axisymmetric and go from there. But in this case, you have your downdraft, your wall jet, where the winds near the ground are very strong. That's where you engineers really care about. And the roll vortex, it's usually right beneath the roll vortex where you see the strongest winds in a downburst. Here is a nice zoom in showing every single grid point. I remember making this figure, by the way. It was a long time ago, but I was very proud of this figure. The reason being, this will be in the supplemental material, but the model that ran these simulations was a homemade supercomputer made by my advisor and one of his students. And I did I've done some videos on this talking about it, but it was very satisfying to get this done. And that was the highest resolution kind of work being done at the time. I've kind of kept that theme going in my career. I'm still always trying to do the highest resolution work that's ever been done when it comes to thunderstorms. So, all right, I said that was a nice axisymmetric simulation, right? So why don't we do something to make it more like the real atmosphere? Because the real atmosphere is messy. So the first thing I did was let's actually have the cloud that's producing the microburst move, because they don't just sit in one place. Very rarely do you have a thunderstorm that just dumps something on your head for 2 hours and doesn't move. There's always wind shear. There's always wind. So let's say we have a storm that's dropping a microburst, but it's moving. So I translated the cooling source, and that led to downbursts that didn't look symmetric, and that's because we're trying to get that. And so here is a surface, so this is XY plot at the surface of the strongest of the winds at the surface as represented by those vectors. In this case, the microburst cooling source is moving towards the east, so it's moving towards where the arrows are the strongest. And it turns out that, yes, indeed, as you might think, the winds are stronger in the direction of the cloud, the direction the cloud's moving. That's where your strongest winds, the direction of your strongest winds. Because you're adding on the translation velocity to what you'd get if you drop the downburst. The only thing about that is true to a point. If you move it too fast, you end up getting something that is actually less damaging. So here is a vertical cross-section through one of these moving source microbursts showing you the vertical winds. You'll notice the downdraft is not entirely erect. It actually has winds that are falling and also moving to the east at the time. And you'll notice there's a hint, there is a roll vortex way off to the left there. If you look at about 2.5 or so kilometers, on the bottom left of the figure, you can see the remnants of the first downburst, or the outflow from the downburst going towards the west. But you'll notice towards the east is much stronger, and that roll vortex is also much closer to the downdraft core. That's a region where you're going to get some very strong winds. And here is the potential temperature perturbation field showing you where the cold air is. It's the same exact view as the last one, only looking at a different field. There is your roll vortex off to the left and the one off to the right. You'll notice off to the left, so these contours are separated in 1/3 Kelvin intervals. The dark lines are 1 Kelvin. So you have 1, 2, 3, 4, about 5 kelvins colder than the surrounding atmosphere at 1 kilometer. So if you just look at that there, you can see, that's going to cause a down. That's going to be, the air is going to fall pretty fast because it's pretty cold. But we're moving the source, and it looks asymmetric. So again, this is a vertical cross-section through a 3-dimensional simulation, and we'll show you the 3D stuff in a second. This is the vertical motion occurring within there. You're not so worried about this as engineers, but notice that the strongest downward winds especially are where you'd expect them to be, right below the coldest cold air in the downdraft. Finally, the horizontal winds. This is the east-west component of the wind, the U component of the wind. Notice off to the left there where our sort of weak vortex is. You've got a outflow about 7 meters per second maximum. That's not so bad. Off to the right, things are a bit different, and you have a maximum of about 30 meters per second. You're now getting into the region of concern, and it's off to the right. So very asymmetric with the strongest winds off to one side. This is something similar to what we saw earlier with one of Fujita's observed cases, and I've squinched down his image to match mine because he used a stretched grid. But notice that's actually to scale now. And I'll be darned, they look pretty similar. Again, Fujita was amazing. He got so many things right. I can't get over it. And he wasn't working with a whole lot, but he did a good job. So, whoops. In this next figure here, what I'm showing is I'm showing the maximum surface winds over time. So I want to show what happens when we did a bunch of, we moved the microbursts at different wind speeds, and I decided to look at what the strongest wind speeds were from these different moving sources. And what we found was, as you, looking at the move 0, 0 case, that's the thick black line, that is your downburst that's axisymmetric because there's no wind shear, there's no winds, period, in the environment. So everything just is perfectly axisymmetric. And you get a maximum outflow of approximately 23 meters per second that peaks around 6 minutes or so. Move the cooling source 3 meters per second towards the east, and look at that. We now have a maximum winds about 27 meters per second, which is actually more than 3 meters per second more. It's not linear. You don't just add on the translation velocity. Getting to 6 meters per second. Now we're almost to the peak. We have an outflow, ground relative outflow from, if you're standing on the ground, you'd be smacked with 30 meter per second winds, maybe 31 meters per second. Let's move 9 meters per second. Now it almost doesn't change, and as you get to 12 meters per second, you're actually seeing a decrease. Part of the decrease has to do with, partly is the air doesn't have as much time to cool. Right, it's being diluted a little bit as it falls because of the way the things work. But there's also more shear, more turbulence that kicks in because of the additional speed. But anyway, all the maximum speeds are faster in the direction of the motion. Looking at the forcing is all, if you look at kinetic energy, you know, what's changing the kinetic energy, which is, you know, think of the magnitude of the horizontal winds or the full winds. The negative region right in the center of the downdraft, well, that's air that's losing kinetic energy because it's decelerating as the pressure dome forms when you have a downdraft encountering the ground. You're basically compressing the air. The pressure goes up, and then it squirts the air off to the side, and then you get your little low pressure region from the roll vortex. But if you just look at the pressure kinetic energy forcing, you focus on the large positive regions. That is where you have the strongest forcing in the horizontal winds. You have very strong, and it's all through the pressure term. You develop a pretty strong pressure gradient, horizontal pressure gradient, and that accelerates the wind in these moving source cases more than anything else. So now we go back to, now we look at some three-dimensional renderings of these downbursts. So this is, it's always been important to me, and this is John Anderson's code did this. He's responsible for the code that made the images. He wrote it himself. But here we have a single microburst, the axisymmetric one, top left. Top right, we have two microbursts that almost overlap in space, and it looks like just one kind of fat microburst. On the bottom left is the most interesting case that I encountered in all of my cases here, which is when they're separated in space by 2 kilometers, and they're separated in time by 2 minutes. In other words, the second downburst is initiated 2 minutes after the first one. So this is the parameter space we played with. We played with space and time. And when they're far apart, they sort of undergo an interaction regime, which is almost like 2 waves passing through one another. It's the intermediate one that's where things get interesting. Now, remember way back when I talked about how Ted Fujita had that beautiful picture of the concentric ring downburst and how he assumed that's what forced Dallas-Fort Worth 151 to crash. Well, in the case where I collide microbursts 2 kilometers apart, where they're initiated 2 minutes apart, notice in the top right, I show you a three-dimensional image. That plane that you see, that vertical plane that's in gray, is the plane that is shown in the vector plot. Now, if you look at this, it looks an awful lot, I think, like Fujita's analysis of that event, only with a single downburst, right? It's deeper than you normally see. You have, I can see 3 suggestions at least of concentric rings, only they're not concentric, they're just like, they look like roll vortex circulations. One's as high as 1 kilometer above the ground, one's about 900 meters above the ground, one's about 600 meters above the ground. This is a different kind of regime than you see with a single downburst, single downdraft. The roll vortices are way too high, the cold air is way too deep. When you have a single one, it almost always keeps all the action near the ground. Now, but if you're an aircraft trying to fly through this, you're going to encounter a downdraft, then a tailwind, then a downdraft, and a super strong tailwind, and by then you might, so again, nobody knows what exactly happened on that day. But I have found my work suggested that something other than what Fujita hypothesized probably happened. We tried really hard to get Fujita's scenario to happen, but it physically just didn't. He didn't have models to test his theories back then. They just didn't exist back then. But it turns out that it was probably something more complex that happened on that day. And here again is his analysis. There's 3, I don't know, it gets me here. There's like 3 concentric things. They're about a few hundred meters, well, like let's say maybe 800 meters above. It's just that the downdraft with the concentric downburst, you just don't get that kind of outflow when you do that. You just get one vortex. So you really do need something more complex. All right, so here we've got about 25 minutes left. I am now going to share with you a short video taken from an old VHS because I don't have the files anymore, that John Anderson put together showing some of a little thing showing our simulation. So here's a subcloud simulation. Here's the parameters. And the blue stuff, that's the cold air hitting the ground and spreading out. So this is the potential temperature perturbation field, and this is the 2 kilometer, 2 minute different data, and you'll notice that you have this sort of a surge of air that kind of squirts towards the north and south of this collision region. So the axis of the collision is along the east-west axis. So you have symmetry, north-south symmetry. So the air going to the south is also going to the north. But you'll notice that, especially in the velocity field, there's a jet that kind of squirts. You have the collision, and then it kind of squirts right at you. And that region is where I put that vertical plane, and that is where we see those high roll vortices. It looks a lot like Fujita's analysis, and it's probably something like the Dallas-Fort Worth 151 encountered. So that's the cooling source approach that we use to force our downbursts. Another common approach, especially in wind engineering, is called the impinging jet approach, which is a momentum-based approach where you have a momentum source that shoots out of a jet that's usually circular jet or it's axisymmetric jet, and you just have momentum, okay, and it blasts the air down, and it does a reasonably good job of producing something that looks like a downburst. Now we did a comparison, or my collaborator Vermeer et al. So this is with work at Western University at the time. Brian Vermeer is now faculty. He's doing lots of really interesting work with downbursts and modeling. But one of the things he did, we did a very high resolution simulation using the cooling source approach, and the darker the trace in these images, the colder the air. You'll notice with this approach, you have the coldest air in the center of this has been split in half, so you're only seeing one side of it. You see the cold air hits the ground. There's a counter-rotating vortex top left. By the time you're at top right, you now have something that looks like this. So you've got your roll vortex doing its thing, but you also have a counter-rotating vortex that formed as a result of frictional interaction with the ground. Then things get messy and it kind of falls apart. So that's the cooling source approach. I'm saying that this is a pretty good way of doing it, especially for buoyant, when you know it's been buoyantly forced from cold air. There's another approach that's called the impinging jet approach, and this one is common, and we've used it as well. And in this paper, what we did was we compared the impinging jet approach to the cooling source approach, as one of our goals was to sort of see how it differed. You'll notice that in the top left image, you already have a full formed roll vortex that is almost like beneath some of the outflow. So this vortex formed along a shear instability after it exited the pipe. And in the top right image and in the bottom left image, you see these shear instabilities along the downdraft. You don't see those in the cooling source approach, okay? You just don't. By virtue of the way we do it, you don't get that shear area. But I will say, the real atmosphere sometimes shows that kind of stuff. If you go back to the third video where I showed the rain falling over the mountains and into the lake or into the river, if you look very carefully on the right of that rain shaft, you see things that look very similar to this. So I can't really knock the impinging jet approach, because it's almost like we should use some sort of hybrid approach, or maybe improve the cooling source approach to make it less smooth, because you sometimes do get those instabilities. But I will say this, you never see what you see at the bottom right. I've never seen anything. Now it just looks like crazy land. All those vortices and such are too strong, they're too compact, they're too regular. You've overdone it with the momentum, and you haven't done it with the buoyancy, and you end up with some forcing that's a little weird. Now, so I don't know. This is an approach that I feel is inferior to cooling source under most cases, but there may be a hybrid approach that might even be the best of both worlds. I don't know. My collaborator might disagree with me on this when I do this work with. Okay, so now here's something we can all agree on. If you can include the real cloud, you're probably going to have a more accurate scenario. So here is a simulation I did a while back. The gray stuff is rain. On the ground, you're looking at the surface wind speed. So in this case, we're actually forcing the downburst just by growing a cloud in an environment where it's conducive for downbursts. So this is a Denver type environment, like that sounding I showed you earlier. I grow a cloud in that environment, and this is what happens. So here's an animation. So you see the rain's falling. You see already there's some hints of some pretty strong air. And then right about now, that's when you see the strongest winds. Right there. It's very transient. It's very axisymmetric or asymmetric. And it's a bit more complex than either one of our cooling sources impinging jet models. It's much more complex. Here's another animation. In this case, we're showing potential temperature perturbation. So this is the cold air. This is one of my favorite visualizations of this storm, because it really shows you what's going on. And now keep in mind the box that the storm is integrated in is much bigger. We're just showing the action sort of. So the downbursts, they arrive at the ground at different times. The air is colder in some areas. There's downbursts coming at different regions. There's downbursts falling on other downbursts. It's pretty complex. And indeed, it's not a surprise to me that you see in the wind field very non-symmetric outflow. You see regions where you have just tiny regions where the wind's really strong, and then maybe even 100 meters away, it's not as strong. So if we use really simplified, smooth forcing, you usually get a pretty smooth, simple result in general. When you start to increase the realism, increase wind shear, things like that, you end up with things that look more real but are a little maybe harder to analyze because they're no longer as simple and smooth as what we started. In science, we love our conceptual models in science. Conceptual models are wonderful, but you got to remember they're conceptual models. It's not like the atmosphere cares about the conceptual models that humans come up with, right? But I sometimes see us falling into that trap of doing our science where we're saying, well, the conceptual model and you know, all these other results from these other scientists all agree that this is a good thing, but sometimes it doesn't actually capture what's going on. So keep that in mind, okay? With your conceptual, know when you're using any kind of model, just make sure you understand the assumptions built in. It's always good to know, not treat it as a black box, okay? That's the last thing you want to do. You want to make sure that you understand the physics so that you're doing better science, better engineering. So here's a figure from a recent paper with Chris Oreskovic and the Western Ontario folks. This is one of our high resolution. This would be a axisymmetric downburst. In this case, we wanted to show the wind field really clearly, and we did some scaling and some other arguments with this paper. But I just wanted to show you sort of what a state-of-the-art outflow looks like from the cooling source approach. This is the winds that are being shown are the U wind component, the radial wind velocity. So the wind along the radius. So you have the strongest winds going towards the east at about 100 meters above the ground, and also right near the ground. The blue zone you see near the ground is the westward motion from a counter-rotating vortex that occurs along the leading edge of this. If I were to just sort of say today, what are the outstanding issues regarding CFD simulations of downbursts, which this talk is about? All of our models designed to directly simulate downbursts are overly simplified. That's okay, though. We need these kinds of models. We need simple models if we can use them as proxies for much more complex phenomena. But be aware that whether you're using an impinging jet forcing, a cooling source forcing, or any sort of other highly idealized forcing, that the real atmosphere is more complex than that. Even if your model is three-dimensional and it results in highly anisotropic asymmetric flow, the real atmosphere is messy. It's not symmetric much at all. There is in atmospheric science, it's still an open question of how to handle the surface boundary condition the most accurately or the most physically faithful to reality. It turns out that the no-slip surface boundary condition, that is the boundary condition of life, basically, namely the ground is solid and doesn't move with the air, you can't use that in a full cloud model and expect to get really good results, mostly because we don't resolve the boundary layer well enough, and by imposing that surface boundary condition, it disrupts the normal life cycle of the storm you're trying to simulate. This is true at least for my supercell simulation work, where you've got strong inflow going into the storm, and if you have a tornado, you have strong inflow, and that inflow is slowed down by that surface boundary condition in a way that kind of messes things up. So what I will say, and the engineers do this better, you guys almost always handle the surface better because you're resolving it really well, and you're using a no-slip surface boundary condition. But you also have the luxury of not worrying about growing the cloud that forced that thing in the first place. It's easy to drop stuff down onto a no-slip boundary condition. I can do that in a heartbeat. But try growing a cloud and then having it all come out. So that's a challenge, say, of the full cloud approach that I use. This will get easier over time as resolution increases, I think, anyway. You just need to have the surface layer have more grid points in the vertical. And the computational expense of running a full cloud model. In 2021, you can do what I did in 1995 on your cell phone, or even more, okay? That being said, so in other words, to be accurate in almost all cases, you need to use the latest computational hardware that you have available to you. But you don't always need to run the highest resolution simulation you can. In the case of downbursts and stuff, I think once you get down to a few meters or so, you probably don't need to go any further. We're getting closer. We're getting closer to the point where we'll be able to run very complex physical models where we can let the flow evolve in a very natural way, but it's very computationally expensive. I have spent most of my academic career trying and being successful at getting access to the world's most powerful supercomputers that are designed for basic science. I've used the Blue Water supercomputer to do work on tornadoes and supercells, and I'm currently using the Frontera machine at the Texas Advanced Computing Center in Austin, Texas, to do the same kind of work. Not everybody has access to these machines. I understand that. So not everybody, even if they wanted to, could do some of the work that I do because there's just not enough computational resources out there. But I always encourage scientists and engineers to run at the highest resolution they can get away with, so that you don't. If your grid is too coarse, there's too much energy at the subgrid scale, and you're just guessing at what's happening at the subgrid scale. So if your subgrid scale is in the region of what you're interested in, you need to run at a higher resolution, but it does cost you. Now there's some new interesting techniques coming out. In fact, I look at Brian Vermeer again, some of the work he's doing. There's new numerical techniques we can use that might actually make it a lot easier to do some of these things. So those of you who are in engineering, who are interested in CFD, who really like the modeling aspect of it, there is techniques that haven't even been designed yet to do numerical techniques. There's almost an infinite number of ways to discretize or do your mathematics. You know, you can create, there's some people who dedicate their careers towards creating new numerical techniques. So in other words, we have to estimate the solution to these nonlinear partial differential equations that define the future state of what we're looking at. And there are some techniques that may actually get us closer to being able to do things that I couldn't even dream of, especially with GPU hardware and things like that. So, but anyway, it's hard to run a full cloud model to study downbursts. It's not a trivial exercise, but I do it. And if you want to do it and you're savvy and you got a good computer, all my source code is available on GitHub. That'll also be on the supplemental materials. If you really want to go nuts, you can. And there's just uncertainty. Microphysical uncertainties, I would say there's uncertainties in the way real clouds work. In other words, you know, when you consider what a real cloud is, it's gazillions of cloud droplets of different sizes. You have pieces of dust that serve as nuclei for these things to form in the first place. There's countless numbers of collisions and all sorts of things going on inside of clouds. So we really aren't sure exactly how all those processes work together. We know the thermodynamics and, you know, there's certain limitations to what could happen in there. But even putting aside the uncertainties or even considering the uncertainties in real clouds, our parameterizations, the code that we write is even worse because we don't have snowflakes, raindrops, and hailstones in our models. We have mixing ratios of those quantities, which are single value in a grid zone. So if you have a grid box that's 50 meters on a side, it's got one value of mixing ratio for, say, hail. It could have 7,412 hailstones of different sizes in there, but it's represented by a single number. That is the mass of all that hail in that zone divided by the mass of the remaining air in there. So a higher mixing ratio means more hail, lower means less, but it's different than having actual hailstones, right? You just don't, because that's just not the way these models work. Until we get models that are super high resolution, like, we're talking centimeters, or we come up with particle models, and that's probably what we'll end up doing, where you just forget the grid at all, and you just do Lagrangian analysis. That's something that is coming down the pipe. It's going to be an interesting time for simulating clouds and in the future. And while this is kind of far removed from wind engineering work with downbursts, know that when the meteorologists improve their cloud models, it's going to improve everything else about clouds. Okay, so maybe a little bit more accurate forcing for your cooling source model, or even your impinging jet model if you study real clouds in the cloud models. Wet downbursts are less well understood than dry. The dry downbursts have a nice, clean, physical way to look at them. That's why the cooling source approach is how a dry microburst looks like in my mind, and it's easy. It's a buoyancy. You just have negative buoyancy, and the air falls pretty much without having to be slowed down, because the atmosphere is dry neutral, dry adiabatic, and that buoyancy, or that negative buoyancy, is converted, that potential energy is converted to kinetic energy, and you get your winds. But the wet downbursts have some of that going on, but there's also just by virtue of the fact that you have a very intense local rain shaft. So and it's important that it's, not just it's raining heavily everywhere, because then there's no local gradients in the downburst. You need to have, it appears, within your thunderstorm cloud, something like what Fujita showed with his concentric rings, but not exactly. But you can have a cloud that's got a thunderstorm rain. It's kind of gusty, but then within there you have this shaft of very, very heavy precipitation. Chances are that shaft of rain and hail dragging the air down is going to force a wet microburst. Any additional thermodynamic support that you can get by virtue of evaporation or melting will help your downdraft. But the wet cases are not as clean as the dry. There's no simple conceptual model for a wet downburst that I've encountered. There's no nice way to simulate a wet downburst like there is for a dry downburst, at least with our simple models. There's certainly things you could do. I'm sure you could just, like what Proctor did way back when, introduce hydrometeors into the top domain. That's probably the best way to do it, to improve upon, say, the IJ and the CS approach. And then, as I think about it, that might be something I do someday. I'll try to do that. Okay, so some closing thoughts as we round things up here. First of all, thank you for your attention and your time. It's very odd to be giving this lecture in 2021. I had really hoped to come down in March of 2020 and see you all and see Giovanni Soleri and everyone. That didn't happen, but thank you. I want to say that up front. I hope you've enjoyed this, and I hope you've learned a bit. This talk is going to be available on a link that I give you at the end of this talk, along with some supplemental materials. And if you have any questions, I'll be answering them at the end of this talk, but I'm also happy to answer your emails or any way you want to contact me. But let me sort of close up here on this lecture on CFD modeling of downbursts. So I would say, as a human being who at least used to fly a little bit in aircraft before the pandemic, wind shear related aircraft crashes are extremely rare. We've figured that out, and that's great. So I always feel good when I fly. I'm not worrying about downbursts. Downbursts and non-tornadic straight-line winds cause considerable damage in thunderstorms. So in other words, just because the FAA is satisfied, the Federal Aviation Administration of the United States, which used to fund research on downbursts, now they don't need to because we understand them. So just because the aircraft hazard piece has been sort of kept taken care of, doesn't mean the downbursts still aren't interesting. From my perspective as an atmospheric scientist, they're interesting because of the kinetic energy they produce. That's the same interest wind engineers have too, but you guys are more practical, and you're like, all right, let me take that thing and interface it with my structure model and see how the force and the pressures that are acting upon a structure, so that we can design them better, so that the twisting motion of or there's some sort of specific forcing that a downburst causes to a structure. You guys can go out and potentially design a building that is better able to take that type of torque or forcing or whatnot. But they're still important to study physically because of the damage. I will say one word about climate change here. I'm an atmospheric scientist. I don't know whether we'll be getting more downbursts in a warming climate. Certainly, there is an argument to be made for we're going to be encountering more and more intense convection, intense rain, intense long falling rain. In other words, events where there's an awful lot of rain falling awfully quickly. So if I were to just spitball it, I'd say the chance of more wet microbursts coming is potentially getting higher, but I don't know. More thunderstorms would probably lead to more downbursts, but the details of that, I don't know. But I will say that we don't really understand the wet downbursts as well as we do the dry because they're more complex and they're often embedded in very messy situations. Concerning some closing thoughts on CFD in general, modeling in general, your model is only as good as the assumptions that are built into it. And don't forget that. I love my models. I use them all the time. They're wonderful things. I think they're helping us learn about the real atmosphere. But as an atmospheric scientist, I am keenly aware of the fact that if something occurs in a model and it hasn't been detected in the real atmosphere, then it is under great suspicion until it has been detected. Thankfully, a couple of things that I've discovered or my research team has discovered in numerical models has actually been found in the real atmosphere. So I'm very much a proponent of this approach. But know that you may find something in a model that is an artifact that doesn't actually exist. Your model is only good as the assumptions that are built into it. And as a physical scientist, I would encourage you to know the assumptions built into your model. Don't treat it as a black box. Cooling source models offer physical advantages over impinging jet models, but both are highly idealized. For the impinging jet model, you just don't have buoyancy forcing. It's a barotropic atmosphere, so there's no thermodynamics. When you introduce thermodynamics, you get a buoyantly forced downdraft. It's likely that the general dynamics after that forcing are going to be more true to reality. And we've written a couple papers on this very issue. But honestly, I think we can improve both methods. I think we can come up with maybe a hybrid method or introduce hydrometeors. If you introduce hydrometeors, you have to make sure your model has moisture and your model can handle the microphysics. You got to handle that evaporation and melting and all that stuff. So engineering models, maybe not, but maybe a high resolution atmospheric model with good surface boundary conditions could really improve, say, downburst modeling without having to do a full cloud. Full cloud model simulations are now possible. I've shown this. I've done it myself. I've used supercomputers to do it. One of my papers I wrote almost a decade ago, I have to believe a decade later that supercomputer is more like a pretty good computer that you could get today. You probably have access at your university to computing resources that can do work that's pretty high resolution. You can do this, but again, it's not the ideal approach from a wind engineering perspective. The research I do is more in the research world, not the practical world, at least right now. I would like to improve the wind engineering models. I'd like to see them be improved, say, by introducing more physics into them that makes them more physically realistic. But it's possible now to do a full cloud. Then it just becomes a data problem because we have way too much data. So that's another issue altogether. And I'll say that, if you think of, quote unquote, pure science and pure engineering goals, they're often different. You guys have specific concerns that scientists don't, and scientists don't have to worry about things like practical things sometimes. But anyway, getting the physics as accurately as possible is always best. I think we can all agree on that. And we can also agree on the fact that the real world is messy. And that messiness causes all sorts of trouble for whether you're a scientist or an engineer. Makes it fun, though. I mean, if it was really easy, why would we do this, right? If you're a student, you're rolling your eyes right now. Okay. I will now, if everything is working the way I think it will, this talk was prepared Friday. So it'll be Friday, October 1st. And I will pause for questions now in real time. So after the talk's over, I should be available. Now, I do have a bunch of supplemental material or some supplemental material available for you at the link you see below. And this talk is actually also available there as well. So thank you very much for your time. And I will pause for questions. And I hope you have a great workshop, great conference, and learn a whole lot of good stuff. So take care.